we're going to move on. And I'm going to hand over to Paul Spence. For those who don't know Paul, he's at UNSW. He works on ocean models, particularly a global high-resolution ocean model that we're working on. And his job is to tell you all about vorticity and quasi-geostrophy. And he's got a few props, including spinning chairs, extra whiteboards, and I dread to think what will come of this, but we'll let Paul tell you.
Hopefully no one gets injured. That's the primary thing. Hi, thanks. I'm Paul. I am very excited to be here. I was so excited I couldn't sleep last night. And it's because I really love geophysical fluid dynamics, even though I'm not exceptional at it at all. Many people are much better than me. But it's nice to be in a room where we all love geophysical fluid dynamics. It's a very rare opportunity. And I want to encourage you, well, first thank the organizers for providing this opportunity. And then I also want to really encourage you to embrace this opportunity and get involved in what we're doing here. I'm going to demand audience participation. And there are prizes. There will be prizes for certain things. Okay, so please embrace your humility and get involved. We are going to get vortical. I thought of that Saturday night. I thought it was good. I need 2 volunteers. Who's good at spinning? Who's an excellent spinner? There we go. One more, please. Don't be a sissy. 2, thank you. We also need 2 people to come up and provide emotional and physical support. You 2, please. Just make sure that they don't fall, and then you'll have to do something else. Now please, you're in a spinning chair. Do the best you can to spin that chair while doing this.
Like this?
Yeah, maybe start like this, and then go like this. Hold on, let me give you a good spin. So you start in tight, and then put your arms out. Oh, it's not a very good chair. Hold on, try again. Try again. So there's that one? Oh, that's good. Okay, let's go again.
Whoa, geez.
Arms out. Slow. Huh? You see it? You see it? Oh, what is happening? Please tell me what is happening. Feel free to yell out answers. I do not require hands. Pardon me?
Conservation of angular momentum.
Conservation of angular momentum. Thank you very much. Conservation of angular momentum for a rigid body is, that's what we're calling L here. It's the cross product between the radial distance between the center of the angular rotation and the linear momentum, m times v. Okay, or it's also equal to the moment of inertia times omega, which is the angular velocity. So, what's happening as they put their arms out? What's increasing? R. What's decreasing? V or omega. Okay, good. Now, these people are sitting here placidly on their rotating chairs, but something else is happening all the time while we're on planet Earth. What is that? What other rotation is involved?
The Earth's rotation.
The Earth's rotation. How fast are you currently traveling through space? Do you know?
2 pi radians a day?
Yeah. Or 1,500 kilometers per hour. It's fast. It makes buying a Ferrari seem irrelevant. Right? What's an extra couple hundred K? Next time you feel jealous about someone driving a Ferrari, just remind yourself you're already going 1,500 kilometers an hour. Okay, but this whole conservation of angular momentum, right, that applies to all Newtonian rigid bodies. So while these people are spinning on their chair, you also have to consider the Earth's rotation at the same time. It's coming into the play of conservation of angular momentum, yeah? F is being involved. Now, when Matt was going through his lectures, F was always being multiplied by something else, right? When is F irrelevant? The Coriolis effect. When is it irrelevant? At the equator. And when else? When there's no velocity. Exactly. So this little demonstration, now we need our support staff and maybe a bit more space.
Get out of the way.
No, you're coming back here. And you're coming back here. Yeah, well, I've never done this before. I have no idea if it's going to work. That's true, I've never done it. And you are going to come behind them. Come here and come here. So all we're going to really do today is consider someone rotating on a chair while rotating on planet Earth. Like we're going to feel vorticity right now. You're going to feel it. While moving, because F doesn't matter if you're not moving. So what I'd like, this is not going to work.
I'm not sure I should do this. I broke my wrist.
Yeah, you shouldn't do this, no. Yeah, I'm really serious. You shouldn't.
Yeah, team.
Ross, get in there. So you were our best spinner. Thank you.
About your wrist there.
So this is really the essence of vorticity. I just invented this, and hopefully no one gets hurt. It could become unstable, right? Instabilities. I want you guys to rotate in your chair, right? Just do a rotation, and then I also want you guys to push them.
Clockwise or anti-clockwise?
I don't care. So maybe we start with the push, and then you guys try to give some spin as you're going. Okay, this is all that's happening. There we go. Give them a good push. Maybe a running push. 1, 2, 3, spin! 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 Okay, I think that's enough of that. That's really... Do you want to try again? Or you want to go again? All right. Go again. So, 1, 2, 3, push, 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 spin, spin, spin! Excellent. Thank you. Thank you very much. Oh my goodness. So that's really the essence of the next 55 minutes. Okay, we're talking about conservation of angular momentum and how does it work on a moving sphere, this rotating sphere, okay? So that's essentially what we're talking about is vorticity. Vorticity is a quantity related to the amount of rotation in the fluid, or really, what we're really going to start off here is the local rate of angular rotation, okay? And this quantity, this vorticity, determines whether fluid particle rotates as it's traveling through the medium, okay? And it's a vector, okay, omega, and it's just equal to the curl of the velocity field, right? Okay, and so you can imagine the curl of the velocity field, you can just write down as this matrix here, I, J, and K components, derivatives with respect to X, Y, and Z, and then the U, V, and W velocity fields, right? And then there's going to be 3 components to this, an omega in the X direction, an omega in the Y direction, and an omega in the Z direction that are equal to these terms here if you solve this cross product matrix. Does that make sense? And so if we take a simple example here, where if you have a shear in the flow, okay, that's going to induce a sense of rotation or vorticity to the particle. That's really the essence of what we're doing. And it is a vector, and the direction of the vector is determined by the right-hand rule, right? So in this case, the rotation is like this, so the vector is directed into the board. That's the direction of the vorticity vector. Check. Uh-oh, I'm running on reserve battery power. There we go. I think that is resolved. So one of the things that's interesting about geophysical fluid dynamics is the aspect ratio. Does anyone know what we're talking about when I say aspect ratio? What is an aspect ratio? Bueller? No? So it's the ratio of the horizontal scale that we're looking at divided by the vertical. Okay, so aspect ratio is horizontal over vertical. And when we're talking about the atmosphere or the ocean, vertical. What's the distance across a typical ocean basin or around the Earth, like 10,000 kilometers or something like that, right? So we'll talk about the ocean, 10,000 kilometers maybe across the ocean. How deep is it roughly? 4. So what's its aspect ratio? It's huge, right? It's huge. It actually has the same aspect ratio, roughly, as a piece of paper. Right? The ocean or the atmosphere, that's really its aspect ratio. This is the horizontal scale, and this little bit here is its vertical scale, if you do the math. So that implies, what it really implies is that vertical motions are small. okay? And that's where we're deriving the hydrostatic approximation stuff. So we're looking at, talking about vorticity, the only one we're really interested in is the one involving the horizontal terms that's directed out of the board. So the Z component of the vorticity terms, okay, which is just this, right? And again, for the right-hand rule, if you're in an X, Y framework here, and this is your velocity vector, so there's a gradient in velocity as you move in the X direction, inducing a positive vorticity directed out of the board. Or in this case, again, Y gradient going this way, inducing a rotation, a negative vorticity. Straight up. Now, what we're calling is circulation and vorticity are closely related. The circulation is defined as the integral around a closed loop, okay? It's around a path, a closed path of the velocity field, okay? That's the circulation. And if we follow Stokes' theorem then, and just take the circulation of u dot dr, we can apply Stokes' theorem and turn that as an integral over the interior area, right? Simple Stokes' theorem. And then if you assume that that area gets really small, this curl, this vorticity curl, can come out of the integral, right? So in that sense, you can really just define the local vorticity as just the circulation divided by the unit area, okay? As an essence of vorticity. So let's do some examples here. We're going to start off with a 2D linearized flow where u is a function just of x and y. Okay, and the curl is just going to be in the xy direction. And take out your pens and paper. Let's do it. Pens and paper. Actually, let's make it worse, because I used to have to do math on the board in front of other people. And so, who wants to embrace their humility and do this up in front of other people? We'll do it as a group of 2. Don't be afraid, it's just math. No one's ever gotten hurt by getting math wrong. Okay? You're not going to hurt anyone if you get this wrong. And it's going to be simple. You're just going to take a little derivative. Come on. Put your hand up. Sir? Yeah? Would you like to come up and help? Anyone else? Don't be a bunch of chickens. It'll be okay. It'll be okay. You're just going to differentiate. No one? You only get chocolate bars for asking questions. So, yeah. Someone, please? Yeah, come on up. You too, you're going to be fine. It's going to be just fine.
Come on, Laura.
It's going to be just fine. Even if you get it wrong, it's okay. We'll love you more for it. It's going to be okay. It's going to be okay. Okay, so what I would like you to do is consider this equation. Write this down on the board. U is equal to kx and v is equal to minus ky.
I do have the world's worst handwriting.
No, it's good. It's better than mine. And then I would like you to solve for this z component of the vorticity. So take dv by dx.
Just going to write it down.
Minus du by dy. Exactly.
So dv dx is 0.
0. 0 equal to 0. And what is our vorticity? 0. Exactly. It's just going to be a straight line flow where there's no shear in it at all. Just linear, no vorticity. Excellent. Let's do example number 2. See, it's not scary.
I just got the last one wrong.
It's not scary. It's not scary. I'm going to make it harder soon. Don't worry. Now, in this case, we're going to have u is equal to ky, v is equal to minus kx. And then I'll bring up that w equation again for you. Oh, good, because I get it wrong all the time.
Okay. dv dx minus k.
Yeah.
dv is k.
Minus 2k. Excellent. Thank you very much. Perfect, right? This one has a vorticity. And if you do a little bit of trickery, okay, so u here is just dx dt, v is just dy dt. You can, dt is common, substitute some things out, you'll find out it's just the equation of a circle, okay? So in this situation, the flow is being driven by, so the flow is circular, okay, and that's what initiating the vorticity in the fluid. Now, we're going to do a little one. How slow am I going? I'm going pretty slow. Okay, thanks for your help. Thank you very much. You do get a prize, which you have to share, because I'm expecting more questions.
Oh, thank you.
I'm expecting more questions. Now, let's consider, geez, I hope I have time to go through all this, because I'm, example 3. In this case, we're going to look at a fluid undergoing a uniform rotation. Rotating is a solid body with a uniform angular velocity omega. Does that sound familiar to anybody? It's kind of like Earth, right? A sphere moving with, sorry. So here's the example, right? We have a rotating sphere with an angular velocity omega naught. There's a radial distance coming out here, okay? You can then project that as having x and y components, right? In this radial direction like this, okay? And so u, the velocity, is just going to equal to omega cross r, which then we can write as a matrix again. I'm going to need more room, j and k components. For the omega term, it's only a function of in the k direction, so this is going to be 0, 0, and omega naught. And then for the x and y terms, x, is just r cosine theta, where theta is your latitude here, okay? This term here is just r sine theta, your y component, and this is 0. So if you solve through here for your velocity, you're just going to get u is equal to minus omega r sine theta I hat, which is just if you look at these terms, yeah? And then the other one is just going to be plus omega r cosine theta j hat, which is just if you look at, these terms. Yeah, and then the k one is 0 because they're both multiplied by 0. Check. Okay, now we want to look at wz of this, right? Which is just dv by dx minus du by dy, right? So we can write that, well, I'm running out of space already. We can write that as another matrix. Can you guys, anybody see this? Yeah? Okay, sorry. You can solve that as a matrix of just I, j, and k over your x component now is omega r sine theta. Your j component is omega r cosine theta. K is 0. And then we have d by dx, d by dy, and d by dz. Yeah? So we're just going to now take grad cross u is equal to this, right? And solve that. Does that make sense? Now, if you do that, all that's going to come out is you're going to have d by dx of omega r cosine theta plus, no, is that d by dy. d by dx of omega r sine theta, right? Omega naught is just a constant. R is just r cos theta is just equal to x, right? R sine theta is just equal to y, yeah? d by dy, if y is 1, this is 1, and you're just left with 2 omega. Okay, so that's the answer for that. But the key is omega has 2 parts to it. It has an omega cosine theta j plus an omega sine theta k. And what's the part that we only care about on planet Earth? For the most part. It's just the k term, right? So really, this gets simplified to 2 omega sine theta. Yeah? And what does that look like? That's the Coriolis parameter. Good? So that's your planetary vorticity. Excellent. Now, we're going to derive the vorticity equation next up. The first thing we need to do So Matt did a lot of time talking about geostrophic flow, okay, where there's no time derivatives, there's no advective derivatives. So we're going to bring in this material derivative. And I'm sure a lot of you are very familiar with it. I still like this schematic because I think it's great. It's a great explanation. So your material derivative here is this expansion for a particle moving within a moving flow field. So if nothing's moving in the flow field, your whole material derivative is 0. In this scenario, there's no change in the velocity in the x direction here coming this way, right? The velocity is constant in x, but it's changing in time. So your first term of the material derivative here is not equal to 0, but any of these du by dx terms are going to be equal to 0, okay? So that's what's happening there. It's kind of like, well, I'll get to that analogy in a second. In this situation here, there's no change in time, right? But the flow field is moving, is changing in space. It's accelerating, it's decelerating as the channel widens. So in this case, this is equal to 0, but this is not. And here's where everything's happening, okay? They're both not equal to 0. To me, it's kind of analogous, and I'm not even sure how accurate this is, but it's like being in a canoe in a river. Okay, you can be floating down the river, and the river could be getting wider and narrow and speeding up and slowing down because of that, but you might not be paddling. Or you could be in a straight river and paddling. Okay, they're both ways of having it happen. Okay, now we're going to do more math. This is going to be the hardest part that you're going to have to do, and it's okay. We can do it. We're going to derive the potential vorticity equation. I think if people could get into partners, that would be great. So find a partner who's beside you. You're going to do it. Yes, you are going to do it. Okay? Get a piece of paper. Do math. It's good for you. I hadn't done this in ages. It was annoying. That's what I spent my weekend doing it. So are you. Okay? Get out. Paper, gentlemen. Just because you're old doesn't mean you can't do math. Let's go. I agree. It's true. So, gentlemen, where's your paper? Good? Oh, he's doing it on his iPhone. And can I get a couple volunteers to come up here and do it on the board? Don't be afraid. It's going to be just fine. I'll give you the answers. It's going to be okay. Who'd like to come up? It's okay. Alice, come on up. Alice and Chris, all you got to know is the product rule. That's it. This is the only thing you got to know. This is the product rule. And you got to wipe off the boards. Okay, so the first thing I would like you to do okay. Oh, we got 3 people. Perfect. Perfect. Good. Thank you very much. Still no. Okay. We're going to start with these momentum and continuity equations. Okay. We're doing a few basic assumptions first. One, the fluid is inviscid. There's no friction. We're going to drop friction out of the party. We're also going to assume that it's constant density. Okay. So there's no density variations. It's just constant density ocean. Okay. And that kind of means, as Matt said, that the only terms regarding pressure that matter are changes in sea surface height. Okay, they're the only thing that are going to determine pressure terms. And here, we're determining changes in sea surface height as a function of eta. That's eta, yeah? Of x, y, which is a function of x, y, and t. Okay, so your horizontal momentum equations are just this, your material derivative, your Coriolis term, and changes in pressure due to changes in height. And we still have the continuity equation. So, what I would like you to first do is write down the continuity equation. Go ahead. Write it down. Yep. Write it down. And then the next thing I would like you to do is integrate the continuity equation over depth. So take du by dx, dz integral. Okay? And do it for each of these terms. dv by dy, dz integral. Yeah. So now integrate that with respect to z. Just draw it out first, and then we'll solve it in a second. Yeah, just put du dx, and then dz in there. Yeah, do it bit by bit, and then dz. Exactly. All 3 terms. Thank you. Oh man, there's no way we're gonna get through this. Perfect. Okay, now remember that u and v are independent of z. So try to go through there and solve that integral. And the bounds of your integral here, sorry, I'll speed it up. People writing this down, trying to do it. U and v are independent of z. So you can bring the du by dx and dv by dy terms out of the integral. Right? And you just have an integral of dz. Yep. Are people getting to here now? You good? Yeah. So you can just solve for z now as eta plus h, right?
Okay.
Yeah. It's just that's the boundary conditions there. And then the next thing you want to do is just this one, the dw by dz term, you're going to have to integrate. Okay? And so w at the surface here, right? We can just expand that out. At the surface, it's just going to be the material derivative with eta being the sea surface height. Okay? This should say at the bottom. I'm sorry, it doesn't. It should just say at the bottom. But the w expansion at the bottom for the eta minus h term is just going to be, again, that material derivative. Good. Perfect. Now we're just going to jump ahead a little bit in the interest of time, but thank you very much. Again, at the surface for w minus eta, it's just going to be this term, the material derivative, and at the bottom, should say at the bottom, it's just going to be this term. Okay? And so if then we start, we substitute these, the surface and the bottom terms into there and do a bit of an expansion. Okay? What you end up with is something that looks like this. Okay, where d is your big material derivative. Are people following that? Yes? No? A little bit? Okay. Now, keep that on the side. We're going to use that again in a second. And what we're going to do next is take, and I'm sorry, I don't think we're going to have time to do it. My great dream of having people do this on the board is crumbling as the clock ticks. Because it is a little complicated, okay? But all we're going to do now is take d by dy of the u momentum equation, which is, sorry. We're going to take the y derivative of this equation and the x derivative of this equation and subtract them. Okay, that's it. So d by dy of the u momentum equation minus d by dx of the v momentum equation. So again, this is your u momentum equation, here, here, and here. Just take the derivatives with respect to y. The v momentum equation, take the derivatives with respect to x, okay, and subtract them. When you subtract them, what drops out? What's going to be the common term here? They're both just going to have g, dy, dx, d eta, right? In both cases. Doesn't matter what order the differentiation is done. So your pressure term is going to drop out, right? And in that case, what you're really left with is this equation here, which has the d by dy of this term minus the d by the material derivative of this term. You have your Coriolis terms, which we've just gathered together. Okay, we put the v by dy term along with the du by dx term here. And then we did a little bit of trickery here to add a material derivative of the Coriolis force. Okay, essentially because f is only a function of v df dy, we can just write it as that material derivative. Okay, just a bit of trickiness. Now, I know, don't worry, it's going to be okay. All I want you to do now is consider just these first two terms. Okay, just the y derivative of the u material derivative minus the x derivative of the v material derivative, okay? You're going to play around with those a little bit. and just expand it. Okay, do this at night over beer. Find your friends, have a beer tonight, and try to do this. You're just going to expand out your material derivative, okay? d by dx of this big term, or sorry, d by dy of this big term is just all this minus all this, okay? And then you're just going to start gathering like terms. Just gathering like terms is all you want. And then particular, the one that we want to gather is this one. What is that one? That's your vorticity term, right? Just want to start gathering up your vorticity terms. Okay? Now, I know we originally called vorticity omega z, and Matt had something, I think sea surface height is zeta. Now we're going to screw you up even more. And vorticity is going to be zeta. Okay? So that term here, we're going to simplify down as zeta. Okay? And then gather up the rest of these little crazy terms. Oh, painful, I know. And what you're going to come down with is something that looks like this. Whether you have the material derivative of the vorticity plus this weird term here. Essentially, that's your horizontal divergence term, multiplied by your relative vorticity, a Coriolis term with divergence, and a material derivative of the Coriolis term. And that's all going to be equal to 0. Then you're going to use this bizarre trigonomic property, okay, or differentiated property, and play around with it. Okay, where A and B, you have this, then use the Quasi-Geostrophy equation, you get to here. Okay, and then you're going to use this trigonometry identity, and you essentially get to this one here, which is where the party starts. Sorry for the pain, but you can do this. It's easy. Okay, that's where the party's going to start here. This is an equation for potential vorticity. It's conservation of potential vorticity. It's this big term here. Okay, again, we're talking for a homogeneous frictionless fluid. Okay. This here is your relative vorticity, okay? This is your planetary vorticity, and this is changes in height. This quantity must be conserved in the ocean, or in the atmosphere, or for a geophysical fluid, okay? A homogeneous, frictionless geophysical fluid. And so what does it mean? If the flow is geostrophic, what term here is 0? If it's a low if we're assuming a low Rossby number flow, which is essentially that the velocities are small relative to Coriolis. Yeah?
Relative vorticity.
Yeah, relative vorticity is going to be 0, right? Because it's got du by dx and dv by dy, right? Those are the terms that when we kicked out when we decided to make the geostrophic approximation, right? We said that those were small. All we cared about was Coriolis and the pressure gradient, right? So if it's a geostrophic fluid, that one's going to be ignored. And then if we also say that changes in sea surface height are small, right, relative to the depth of the ocean, all you're left with is F over H, right, for a geostrophic fluid. Eta's ignoring it. Zeta and eta we're both going to ignore. So for a geostrophic fluid, the flow must obey the advect according to F over H. Can someone put that in a different word for me? What does that mean, essentially? If you were going to map out where geostrophic fluids were going to, where a geostrophic flow is going to move, how would you do it? What contours is it going to have to follow? What's that? Yeah, it has to follow contours of F over H, a geostrophic flow, because of this potential vorticity conservation law. Geostrophic flow must follow contours of F over H. Okay? F over H must be constant. Its rate of change with time must be 0, or its material derivative must be 0. Okay, so let's do another game here. Let's imagine that your flow, again, is still geostrophic, so this is going to be 0. Let's say your flow isn't changing latitude very much. It's confined to a latitudinal band, or narrow latitudinal band. So F isn't changing very much. Then the flow must essentially follow what? What's that? What has to be held constant then? if f is going to be if f isn't going to change and zeta isn't going to change, you have to follow lines of constant of isobaths essentially. Okay. The flow, if the flow isn't going over a wide meridional range, it has to follow isobaths essentially. Okay. Another way of looking at it. So let's take a couple more examples of this. Essentially, we're going to consider situations where the changes in sea surface height are really small relative to the ocean depth, right? So essentially, the relative vorticity plus the planetary vorticity over h must equal some constant with time. Or sorry, it must be constant. Okay, so if you imagine a sphere like this, and for some reason the flow in the northern hemisphere flow and is moving towards the equator, what is decreasing? Yeah, f is decreasing. So what also must decrease? Yeah, you could screw around with h, but here we're going to say that if h is constant, just for kicks. Constant depth ocean. So if f is decreasing, then what must happen to this term? Yes, thank you. Yeah, so if as the particle moves toward the equator in a constant depth ocean in the northern hemisphere, it needs to increase its rotation. It's spinning in the chair. Okay? Now let's take an example now where f is constant. The fluid is moving into deeper water. Okay, so in this case, h is increasing, right? What must happen to the particle's relative vorticity? It must also increase, right? So it's essentially the stretching of a fluid column. It's like the figure skater, right? She's getting in deeper water, she's pulling her things in, she's got to spin more to maintain her conservation of angular momentum. Okay? So the other thing what I'm not going to be able to really get into is, this is h where we're just assuming it to be the depth of the whole ocean. But you can also do the same sort of stories looking at individual layers, like isopycnal layers in the ocean. Okay, and this property is still going to be, in a multi-layered ocean, it's still going to be conserved. Thanks. Okay, we're going to jump into other people's playland here a little bit. You're going to talk about Rossby waves, I think, tomorrow. But we can learn a little bit about it right now. We're going to look at planetary and topographic waves. Okay? And we're going to be in the northern hemisphere. And we're going to start off with a state of rest. Okay? And this is going towards values of higher potential vorticity. So this is f is increasing. Okay? Now I want you to imagine something's perturbed this surface. There's just a little perturbation. So this is north and this is south, okay? We're in the northern hemisphere. Something's perturbed this fluid so that it's moving northward here, right? So its f is increasing, right? What must happen to its zeta? It's got to decrease, right? So it's going to start having a rotation this direction, negative relative vorticity, yeah? Now, in this part of the wave, this part of the disturbance, what's happening to f? It's decreasing, right? Yeah. So in that case, it must have a compensating increase in zeta, in the relative vorticity, right? And it goes along. And so what I would like you to imagine is if these were gears, okay, and your finger was stuck between these gears, what direction would your finger get smashed towards? It's sort of these rotations are smashing your finger towards the west, right? In this direction. Okay? So essentially, this potential vorticity can act as like a restoring force that can create westward propagating waves, westward propagating planetary waves. Okay? The other example is if we have a perturbation where it's deeper on this side and shallower on this side. Okay? So now we're keeping f constant, and we're just going to play with zeta over h. Okay, so in this case, the fluid is being perturbed towards shallower water, right? And to compensate for this to be, as h is decreasing, zeta must also decrease, right? Negative vorticity. In this case, it's getting deeper, zeta must increase, negative vorticity. And again, your finger's jammed in there. These are gears spinning and you have westward propagating topographic waves. Does that make sense? Okay. And then finally, so Matt kind of screwed me over because he promised me he was going to cover the sphere drip balance. And he didn't. But it's okay, we're going to do it now. And I'm sorry, Andrew, I think I'm going to steal just one slide of your party. Yeah. And so we're going to consider ourselves, we're going to solve for western boundary current intensification just using this basic vorticity balance really quickly, okay? Let's imagine, because I'm from the North Atlantic, let's imagine we're in the North Atlantic. Okay, Northern Hemisphere, western and eastern boundary. What direction are the winds in the mid-latitudes in the North Atlantic? What direction are they going? This way, right? Westerlies. And at the equator, easterlies. Okay. The net Ekman pumping there is going to do what? What's the net, what's the curl of the wind stress? So if you have a wind stress going this way and a wind stress going that way, your curl of the wind stress is going to be negative, right? And it's essentially, this is your sphere drip flow here, which again, this just drops out of geostrophy, continuity equation, and the hydrostatic balance. You can come up with this term. Theta here, we're going to ignore that for a minute. This is just your meridional velocity, okay? But the important part here is that for geostrophic flow, which is all this is coming from, F over H must be constant, okay? And so what the curl of the wind stress is doing is essentially shrinking the water column below the mixed layer, okay? It's squeezing H, okay? And to compensate, V, the velocity flow must be directed towards the equator. The flow is going to have to travel towards the equator to reduce its relative vorticity. Does that kind of make sense? Yeah? And so what the winds are doing here is squeezing, it's reducing H. And so the flow has to move towards lower values of F in order to maintain its potential vorticity. Does that make sense? Just for F over H to be conserved. Okay? So the net sphere drip flow in the interior of the ocean, the geostrophic flow in the northern hemisphere mid-latitudes is towards the equator, is you have this weak sphere drip flow. Okay? So you have this weak equatorward sphere drip flow in the middle of the northern hemisphere, North Atlantic Ocean. Now, this must be balanced just because of conservation of volume. It has to be balanced by a poleward flow somewhere else, right? You have a weak equatorward flow in the interior of the ocean. It has to be balanced by a poleward flow somewhere else for conservation of volume. But that poleward flow can't be happening, it can't be geostrophic, because the geostrophic one is an equatorward sphere drip flow, right? So we're looking now for a non-geostrophic poleward flow. And for it to be non-geostrophic, it kind of needs to be outside of the length and time scales of geostrophy. It has to be narrow and fast. Okay, so it's going to be a narrow, fast boundary current away from the interior where geostrophy works, right? And so you have two options. You could have a narrow, fast poleward flow on the eastern boundary, or you could have a narrow, fast poleward flow on the western boundary. But again, it still must obey the rules of conservation of potential vorticity. So on this side, okay, so if you have an equator, a poleward flow here, right, there's going to be a shear with the interior sphere drip flow. Okay, so in this case, your dV by dx is positive. It's going to be greater than 0. Okay? So your curl is going to be like this, coming out of the board. So what's happening here is that the flow is moving poleward. What's increasing? F is increasing, and you're also increasing your relative vorticity, your dV by dx term. So they're both increasing. It's not conserving in a flat bottom ocean. This is disobeying the conservation of potential vorticity law. Does that make sense? Yeah? If you have it on the western side, though, in this case, the shear between the poleward flow and this narrow, fast current, okay, with the equator flow in the interior, in the sphere drip gyre, is inducing a negative relative vorticity. Your your dv by dx is this way. Does that make sense? So it's working on this side, right? F is increasing. It's going to be balanced by negative relative vorticity. You're going to maintain your conservation of potential vorticity. And so we end up with western boundary current intensification. Does that make sense? Yeah? Okay. Great. Now, oh my God, do I only have 15 minutes? Yeah? Okay. Look out, people. It's going to get worse. Right. This is my first time teaching Quasi-Geostrophy, and there's a lot of people in this room that are going to be better at me than this. So just shut up. No, I don't mean that at all. Tell me, please, just speak freely. Tell us where we're going wrong. It's a bit of a pain. This is your geostrophic balance, which is, pretty boring. What does this not tell us anything about? Why is this of limited use? No time. Okay, this is just a diagnostic equation. It's not going to tell you what's going to happen in the future. What else is it completely missing? Yeah, friction, for sure. We're still going to keep ignoring that. It's also, like the velocity terms are very linear, right? This is just a linear equation. We're missing all the nonlinear interactions, right? And so we're going to move into quasi-geostrophy land. We're going to start with the geostrophic equation, and then we're going to end up coming back to potential vorticity, and it's going to get a little ugly. But essentially we're doing this because the geostrophic balance is informative, but it's boring because it's linear and it's diagnostic. Now, quasi-geostrophy, which is essentially meaning near geostrophy, quasi-geostrophy dynamics allow for us to have prognostics, so time derivative momentum equations that you can solve them quickly and include nonlinear dynamics. Okay? Yeah, it essentially allows a rough representative of mesoscale dynamics in the ocean or synoptic variability in the atmosphere that involves relative vorticity and eddies. So it's going to allow nonlinearities or relative vorticity terms. First, we're going to have to start off with a few approximations. I was hoping Matt was going to cover this, but he didn't either. I'm sorry. I'm just picking on you, man. I'm sorry. The essence of the quasi-geostrophic approximation, I think, can come down to this, to these terms. Essentially, all you want to do is do the same scaling analysis that Matt was doing. Okay, so u by dt is just u's timescale over t's timescale. You're essentially going to look at the size of this term relative to Coriolis, which comes up with 1 over ft. And you're going to say that this is really small. And in doing that, you're excluding small amplitude, fast-moving waves, like surface gravity waves, like surf waves, essentially. You're going to exclude those ones, but that's okay. We don't really care about those. You're also going to ignore Ekman for friction, which is the size of the frictional terms divided by the Coriolis term. You're going to say that that's really small. And then the other one you want is this is the temporal Rossby number involving this term, and then you have these advective Rossby numbers, which is sort of just the Rossby number. Okay, so the size of these nonlinear terms relative to the Coriolis term, which is this. And you also want this to be small. Okay? And there's two ways you can have this be very small. One is that u can be very small, so small velocity timescales. And that is really where the QG formulation comes from. But there's other, and we'll hopefully get to this at the end of the lecture, you could also have a situation where both you have a large u and a large L. And that's something called frontal geostrophy dynamics, which are totally different. Okay? But we're going to do this QG formulation. Oh, there's no chance. There's no chance. Okay, we're also going to use the beta plane approximation. Hopefully some of you have seen this before. We already solved for this. F is equal to 2 omega sine phi, right? Which kind of looks like this. You can imagine doing nonlinearities with this is a total pain in the ass. It's pretty difficult, right? Okay, so we're just going to assume that the Coriolis force has a constant, and then it varies linearly with latitude, this beta term. So F is just equal to F naught some constant plus beta y, which is kind of like just drawing a line here and saying you're not covering huge distances. Okay, so this beta plane approximation works really well in the mid-latitudes. The other one we're going to do is the Boussinesq approximation, which Matt alluded to a little bit. So if we have a term like 1 over rho d rho by dx, The ocean density range is like this, right? Roughly 1,025 to 1,028 kilograms per meter cubed. The density variations are really small, right? So if you look at a term like this, okay, changes in density from 1026 to 1 don't matter much, except if there's no change in density, then this term goes to 0, which is kind of boring. So we want to maintain density variations in this term, but we can exclude them here. All right, because it's pretty much irrelevant whether you're dividing by 1,026 or 1,028. Okay? So essentially what we're going to do, where's my slides? Yeah. That's fine. For the Boussinesq approximation, is really what we're going to do, I'm going to apply this to quasi-geostrophy. We're going to divide density into a homogeneous stratified layer, okay, and then variations away from that homogeneous stratification. Okay, so we have a fluid like this, depth scale. This is, the dotted lines here, your background stratification, which is constant, which is only a function of z. It's not a function of x, y, or t, okay? And then you have variations around that background stratification. So this is really just the hydrostatic approximation. This is at equilibrium in the background, okay? The QG doesn't consider how this background stratification is formed, but really all we're talking about is the behavior of motions that are weakly perturbed, so weak perturbations of this rho prime surface, okay? Similarly, we only need to consider P prime, so variations in pressure, as a function of x, y, z, and t, rather than the mean P bar, mean pressure, because the mean P bar is just determined by this. Okay, it's not variable with time. The background stratification is a hydrostatic equilibrium with the pressure at rest. So we're going to go back to our governing equations here, okay? Again, no friction, no diffusion. Use the Boussinesq and the beta plane approximation. You have a material derivative of Coriolis. This is just your u, your xy momentum equation, your north-south momentum equation. What we've done here, however, is now use the beta plane approximation, right? F naught v, beta yv, see that? That's all just subbed in there. And we're ignoring the p bar term. We're just looking at variations in p with p prime. And using rho naught here now because of the Boussinesq approximation. Similarly, the hydrostatic approximation now is just a function of perturbation density and perturbation pressure, right? You still have the continuity equation, and this is going to be your new conservation of density equation here. Okay? Again, we're just using these properties as well. Notice that, okay, so, right, we only have d rho prime by dx because rho bar is not a function of x. Similarly, rho bar is not a function of y, so there's no rho prime terms there at all. Here, we kept the rho bar term, because rho is a function of z. The rho bar and rho prime are both a function of z, but because rho bar is much, much bigger than rho prime, we can just throw away the rho prime term. Okay? So we've got those equations. Now, if you consider low Rossby number flows, and also the beta plane approximation is essentially saying that F naught is much, much bigger than beta y, it gets really boring. So what you really do then, you take these terms, if you do the low Rossby number approximation, you get rid of that one, you get rid of that one, and you're just left with these two, right? These two. Oh. So your momentum equation is just reduced to this. Your meridional velocity and p prime, your zonal velocity and p prime is a function of x and y. Okay, this is essentially just geostrophy. It's really boring. It's a geostrophic state. It's non-divergent. As Matt sort of got into with Taylor columns, because it's non-divergent, you have no vertical velocities. Okay, those Taylor columns, right? The flow must flow around the bathymetry features. You can't go up over them. W must be 0. Okay? That means that there's no vertical movement of those isopycnals in your background stratification and no change in time. It's totally boring, right? We want to make it a little bit more exciting. But what you do then is you separate your horizontal velocities into having a geostrophic and what we're calling an ageostrophic or a non-geostrophic adjustment to the flow. We're just going to add a little bit of a non-geostrophic perturbation to the velocity field. But we're still going to maintain that the geostrophic velocities are just given by the variations in the pressure field. Okay? F naught. So this is the equation for your UG and your VG terms. Okay? But we're still going to have these ageostrophic stuff. And now we're going to get very hand wavy in the interest of time. All I want you to do now is go back when you do this at home tonight. Go back here. Okay? Because this term, we kind of decided it's a low Rossby number flow. So we kind of decided that this one's going to be small, right? We kind of decided that this one's going to be small, right? But we kind of like this term. We said that was the big one, right? This is your geostrophic term balanced with this. So if it's going to be small and the ageostrophic term is small relative to the geostrophic term, you can just put your geostrophic velocity in here. You're just going to put your geostrophic velocity in here. You're just going to put your geostrophic velocity into here. But here, you're going to keep your ageostrophic term. Hopefully that makes some sense. I know I'm going to start to lose you here. This is my fear. Right. So you're going to use UG and VG from these equations, and you put those into your material derivatives and your beta terms. But you're going to keep the ageostrophic component in the Coriolis term. Okay? So you're going to keep it in here. This one and this one. And if you go through and do this substitution, you end up with this like really ugly bastard equation here. Which is, I mean, it's really hard to find some physical meaning in there. But we're going to get to why this is important at the end. The only thing of real interest here is your Jacobian operator. If you haven't seen it before, it's just a mathematical operator that you can play with. Okay, don't be scared of it. It's just a couple of different derivatives. So we've now just subbed those into our momentum equations, you get that. Okay, keep going. Oh yeah, why is that interesting? So we have this V and U here, right? And then the whole thing is in terms of pressure and density. And so you can actually go back. You know what UG is because we've already defined it. You can go back to these equations and actually solve for your ageostrophic velocities. And it ends up being a whole bunch of these weird terms. So it is somewhat useful initially already. You can also take 6 and 7. So we can solve for the velocity terms here, right? Just by isolating for here, right? Just isolate for that. Then you can go to your continuity equation. And if you sub those into your continuity equation, you can get your vertical velocity field. No worries, right? Ugly. I have no idea what, conceptually this is very difficult for me, what that means. But again, you have your J-bar term, and now you have a Laplacian, which again is just an operator, just a mathematical operator. But now we've determined the vertical velocity. Now because in pure geostrophy, in a homogeneous fluid, right, there can be no vertical velocities. It's non-divergent. W must be 0. These vertical accelerations here are just due to the ageostrophic terms in the flow that we've added in, these little perturbations. So those were our momentum equations. We're also going to mess around with your density equation a little bit. And in this case, we can ignore the ageostrophic terms, okay? And just substitute your geostrophic velocity, Vg and Ug, into here. Bit of trickery. You're going to take a Z derivative, use a hydrostatic balance, mess around for like an hour more, to be honest, and you'll get this. Again, bit of a complicated bugger. But we've now introduced what we're calling n squared, which is the stratification frequency. Does anyone know what n squared is, or a conceptual understanding of what it is, the stratification frequency? Yeah, please.
Is that the Brunt-Weissler frequency?
Exactly, yeah. Yeah, what does it mean?
I think it is the frequency that a wave oscillates in vertical.
Yeah. So if we have a stratified fluid, which we have here, right, and something pushes a parcel down into deeper water, it's going to get pushed back up by the surrounding fluid that is now lighter than its surrounding fluid, and it's going to come back up. And it's going to oscillate with a certain frequency. That's the Brunt-Weissler frequency. Okay? Right. So we have two equations now. We've got this from the continuity equation. We've got this dw by dz equation. And then from the density conservation equation, we've got this one. We have two equations, and if you look closely, there's really only two unknown variables in here. One is p prime, or sorry, that should be rho prime, sorry. Is it rho? P. Well, we can get p prime from rho prime. Anyway, so there's two unknown variables. Your pressure variation is p prime, and your shear, your vertical shear here, your dw by dz. So we have two equations, two unknown variables. You can combine them to yield one quasi-geostrophic prognostic equation for p prime, which is this really fun-looking thing. Okay? This term here really is just your vertical stretching term. So whether the column of water is being stretched or compressed, adding vorticity into the flow. So we went through all that rigorousness to come up with this one prognostic equation. You can do the same thing starting with your original potential vorticity conservation equation. And you can transfer the pressure field into a stream function because you're sort of starting with the geostrophic approximation, the low Rossby number flow, so it's non-divergent, which means you can define a stream function psi. Okay, so this is the other route that you can go to get this stuff. And in that case, you'll end up with this term, this equation here, your prognostic Q, where now Q is your quasi-geostrophic potential vorticity, which has essentially three components. Okay? And what does it really mean when we're looking at something like this? Well, people are going to talk about these terms more later in the week. So in terms of baroclinic instability, eddy mean flow interactions. But essentially, if you look at your quasi-geostrophic potential vorticity term, there's three parts, right? This is your contribution via relative vorticity, just the spinning in the chair. This one here is your contributions due to planetary vorticity, so whether you're changing latitudes, okay? And then this middle term is due to stretching or compressing isopycnal layers or sea surface height displacements. So changing, essentially you can think of that as changing your H term, okay? You can also go back now that you have these two equations for Q and psi, your stream function, and go all the way back and get where we started from, your geostrophic velocities, your ageostrophic velocities, your vertical accelerations, and your pressure and density variation terms. So you can go back and solve all those things. And yeah, so that's what people have been doing. They essentially started doing this in the late, it's really the simplest theoretical basis for understanding vertical motions in an Eulerian framework, okay? It was started in the late 1940s, before they had computers, for people to be able to predict the atmospheric state. Essentially, they had lots of pressure measurements, right, from setting up balloons, I guess, measuring atmospheric pressure. And from that, they were doing the geostrophic approximation, but it gave them no forecasting ability. So they started going down this path of adding a little bit of ageostrophic flow to the geostrophic approximation to be able to come up with prognostic equations for the atmosphere. Okay, you can solve the momentums quite quickly while still including nonlinear dynamics. Okay, so we're allowing for nonlinear dynamics to feed into the flow. And it's been used a long time for synoptic scale meteorology and mesoscale ocean dynamics, which I will give you a quick, I know I'm going over time here. I'll stop very quickly. Thanks for your patience. So this is just an animation that someone did for a mesoscale quasi-geostrophic model of the Southern Ocean. Again, you can see a lot of nonlinear dynamics in here. Okay? Smaller scale features than if you looked at in the atmosphere. Okay? But again, straight from those equations, which is beautiful. And then finally, I just would like to quickly say, what are we missing when we start thinking about quasi-geostrophy? What are you really missing? What's the assumption that you're going to screw everything up? Yeah, friction is a big one, yeah, but we're going to keep ignoring that. Yeah, the perturbations are small, exactly. You're sort of assuming that your background stratification is maintained, and the perturbations, your rho prime around that rho bar, are small. And that's not always true at all, especially if you think of the atmosphere. Whoa, where's my, I had another slide there, I lost it. Whoa. Oh no, I'm frozen. So in the atmosphere, most of the precipitation in a lot of places is coming from fronts. So in a frontal system, right, you can imagine a cold front This is cold air. This is warm air. You can imagine this cold front coming across. Because this air is quite dense, it sort of acts like a bulldozer, right? Plowing through. And it demands uplift of this warm air. Okay? This is quite common over North America. And so this is a massive layer transition, right? It's not going to be done well in quasi-geostrophic dynamics at all. And really the energy for these mid-latitude synoptic storms is coming from essentially if you had a bathtub of water with cold water on warm side and warm water on the other side with like a thing in the middle blocking it, and then you took the blocker away, what's going to happen? They're going to flip, right? Cold on the bottom, warm on the top. So there's available potential energy there that you're going to release and turn into kinetic energy. And that big layer movement is not going to be captured by QG approximations very well at all. Thank you very much.